Never assume space is quiet, because what just slipped into our solar system is anything but. So subscribe now, because this story is changing in real time. If you think we've already found the strangest thing in space, don't blink, because what James Webb just noticed near 3I, Atlas has scientists rechecking their own instruments. For decades, we've aimed our best tools into the dark, not to hunt fear, but to find answers. The James Webb Space Telescope was built to study the first stars, distant galaxies, and the chemistry of planets forming around other suns. But during routine tracking of interstellar object 3I, Atlas, Webb recorded something that did not fit any clean pattern astronomers expect from comets or asteroids passing through our system. At first glance, 3I, Atlas, looked like a typical fast-moving interstellar visitor. A faint streak sliding across background stars, picked up by survey programs and then confirmed by teams connected to the European Southern Observatory and the Vera Rubin Observatory pipeline. Interstellar objects are rare, but not unheard of. We've seen Oumuamua in 2017 and 2I, Borisov, in 2019. Each one surprised scientists in different ways, but both could still be explained within natural models of space debris ejected from distant star systems. 3I, Atlas, however, started behaving in ways that made experienced observers pause. Data teams working with NASA's Jet Propulsion Laboratory noticed subtle changes in brightness that didn't match simple dust release or ice heating models. The light curve wasn't chaotic like most comets. It showed repeating patterns. Not perfect, not mechanical, but steady enough to raise eyebrows. Astronomers at the Harvard-Smithsonian Center for Astrophysics pointed out that repeating brightness changes can come from rotation, surface shape, or uneven outgassing. But in this case, the pattern stayed unusually consistent across multiple observation windows. Then came the infrared readings from Webb. Instead of just reflecting heat from the sun the way dusty ice normally does, parts of 3I, Atlas showed thermal behavior that suggested internal structure differences. Not heat being generated, but heat being held and released in a way that didn't match simple models of loose rubble or porous ice. Scientists working with Webb's data teams compared these signatures with known comet profiles and found mismatches. Not proof of anything strange, just enough difference to say, this one isn't behaving like the others we've cataloged. At the same time, spectroscopic readings from instruments tied to the Keck Observatory in Hawaii and follow-up analysis using legacy Arecibo data models showed something else. The dust tail of 3I, Atlas, was behaving unevenly. Normally, sunlight pushes dust away from the sun in predictable ways. But this object showed dust distribution that suggested localized jets or surface features directing material in narrow streams. That can still happen naturally, but the consistency of where the material appeared over time was what made it stand out. As more data came in, teams across NASA, ESA, and independent university groups began sharing notes. Not in public statements, not in dramatic press conferences, but in quiet papers and internal discussions. When multiple groups start noticing the same odd patterns independently, that's when science gets curious. Not excited, curious, because curiosity means something doesn't quite fit yet. One researcher connected to Stanford's radio astronomy program referenced Ronald Bracewell's old work on how advanced probes, if they existed, would likely stay quiet and blend into natural space traffic. That idea isn't treated as truth in astronomy, but it exists as a thought experiment. The point wasn't that 3I, Atlas, is anything artificial. The point was that our models of interstellar debris are still thin. We've only seen 3 confirmed visitors. 3 data points is not enough to define what normal even means yet. And that's the uncomfortable part. We're trying to build rules from exceptions. Oumuamua didn't behave like expected. Borisov surprised researchers with how fast it broke apart near the Sunday. Now, 3I. Atlas is adding another strange data point. None of this proves anything unusual is happening, but it does prove our picture of what drifts between stars is incomplete. As Webb continued to track faint infrared changes over several observation windows, one pattern became hard to ignore. The way heat shifted across the object's surface suggested layers, not just a loose pile of ice and dust. This doesn't mean technology, it means structure. And structure changes how scientists think about how this object formed in another star system long before our sun even existed. This is where the story gets interesting, not because of aliens, but because of timing. 3I. Atlas is passing through our system at a moment when our tools are finally sensitive enough to notice fine details. The Hubble spectrograph can catch visible light changes. Webb can see thermal behavior. Ground observatories can measure polarization and dust patterns. Voyager 1, still sending telemetry from the edge of the heliosphere, helps scientists understand how the solar wind environment is behaving as this object moves through it. All of that together creates a rare window, not to confirm anything dramatic, but to test what we think we know about interstellar objects. And right now, 3I, Atlas, is quietly reminding astronomers that space still writes rules we haven't learned how to read yet. And this is only the beginning of what Webb is starting to notice about how this object reacts as it moves deeper into the inner solar system. Because the closer it gets to the sun, the harder it becomes for simple models to explain what its surface and dust behavior are doing next. As 3I, Atlas moves deeper toward the inner solar system, its path starts to matter just as much as what it's made of. Objects coming from outside our system usually arrive on steep angles, cut through once, and are gone forever. That's exactly what makes them valuable to scientists. You don't get second chances. Miss the window, and the data is gone for good. Orbit specialists working with NASA's Jet Propulsion Laboratory began mapping 3I, Atlas's trajectory, using updated positional data from ground-based observatories tied into the European Southern Observatory network. The orbit was hyperbolic, which confirms it didn't form around our Sunday. It came from elsewhere, likely ejected from another star system millions or even billions of years ago. That part is expected. What wasn't expected was how closely its path lined up with the inner planets. Over a relatively short time window, 3I, Atlas, passes through a corridor of space that brings it near the orbital neighborhoods of Mars, then Venus, and later out toward Jupiter's region. In cosmic terms, this is still far away, but in trajectory planning terms, it's a tight thread through the busiest part of our planetary system. Engineers at JPL use similar math when plotting gravity assists for spacecraft. Voyager's grand tour wasn't luck. It was precision math. Seeing a natural object pass through a similar geometric corridor doesn't mean design, but it does make scientists pay attention because the odds of multiple closed planetary alignments on a random interstellar pass are low. Harvard-Smithsonian researchers ran statistical models comparing 3I, Atlas's path, to millions of simulated interstellar trajectories. The conclusion wasn't that the path is impossible. It's that it sits on the edge of what we would expect from random motion. Rare doesn't mean artificial. Rare means informative. It hints that the population of objects wandering between stars may be more structured than we thought, shaped by how planetary systems eject debris during violent early stages of formation. Then comes the timing problem. When 3I, Atlas, reaches its closest point to the sun, the moment when heating, outgassing, and surface changes would be at their strongest, it moves into solar conjunction. From Earth's point of view, it passes almost directly behind the Sunday. The glare blocks optical telescopes. The heat overwhelms sensitive instruments. Even the James Webb Space Telescope has strict pointing limits near the sun to protect its mirrors and instruments. For several critical days, our best tools go partially blind. This isn't a cover-up. This is physics and hardware limits. But it creates a frustrating gap in the data, right when scientists would want the clearest view. Similar blind spots have happened before with comets and near-sun asteroids. But because interstellar visitors are so rare, losing this window feels like missing the best page of a book you may never get to read again. Researchers at the Keck Observatory and teams working with Hubble spectrograph have already planned coordinated observations before and after conjunction. They're looking for changes in composition, brightness, and dust behavior that might hint at what happened during the hidden phase. Did it flare? Did it fragment? Did new jets open on its surface? Those answers won't be seen directly. They'll be inferred from what changes afterward. This is where the mystery tone creeps in for the public. Not because something strange is happening, but because humans hate gaps in stories. When there's a blackout in data, imagination fills the space. In reality, astronomers deal with these blind spots all the time. Solar probes, like Parker Solar Probe and Solar Orbiter, face similar constraints. You can't point sensitive instruments directly at the sun without damaging them. Even the most powerful observatories have limits. Meanwhile, independent sky surveys tied to the Vera Rubin Observatory's early data pipelines have been digging through pre-discovery images. This is called precovery, finding an object in older images before it was officially recognized. The longer the observation arc, the better scientists can model the object's true motion and behavior. Early precovery frames of 3I, Atlas suggest its brightness pattern has been stable for longer than first thought, which supports the idea that its odd behavior is intrinsic, not a sudden fluke. As data analysts layered these results with infrared profiles from Webb and polarization readings from ground-based telescopes, one picture started to form. 3I, Atlas likely isn't a loose snowball of ice and dust. It's more compact. That could mean a dense comet nucleus, a fragment of a shattered planetesimal, or debris from a collision in another star system long ago. Each option tells a different story about how violent planetary systems can be. And here's the bigger picture most people miss. Interstellar objects are time capsules. When you study one, you're not just learning about a rock. You're sampling chemistry from a different star system. Researchers at the Harvard-Smithsonian Center for Astrophysics and teams analyzing data through ESO have pointed out that measuring isotope ratios in the water and dust from these objects helps test how common Earth-like chemistry is across the galaxy. If the ratios differ wildly from our comets, it suggests planetary systems can evolve with very different chemical starting points. If they're similar, it hints that the building blocks of planets and oceans might be common. Voyager 1's telemetry data still helps scientists understand the boundary conditions of the heliosphere, the bubble our sun carves in interstellar space. As 3I, Atlas crosses into regions influenced by the solar wind, changes in how its dust behaves help researchers refine models of how interstellar material interacts with stellar environments. That's basic science, with huge implications for understanding how matter moves between stars. So right now, nothing about 3I, Atlas, proves anything strange. What it does prove is that the space between stars is not empty and not simple. It's filled with debris from ancient systems, shaped by physics we're still learning to model. This object is just close enough, just bright enough, and just unusual enough to expose the limits of what we thought we understood. And as it slips closer to the sun and toward that frustrating blind spot, scientists are bracing for the moment when it disappears from clear view, knowing that whatever changes happen there will shape every conclusion they try to draw afterward. When 3I, Atlas, finally begins to emerge from behind the sun, the first thing astronomers look for is change. Not drama, not mystery, change. Because change is where physics shows its hand. If the object flares brighter, fragments, grows a longer tail, or suddenly vents gas, those shifts tell scientists what it's made of and how stable it really is. Teams coordinating observations between NASA's Jet Propulsion Laboratory, the European Southern Observatory, and the Keck Observatory time their measurements down to the hour. The goal is to compare before and after snapshots, like a medical scan. Same object, same instruments, different moment in its journey. Any difference becomes a clue. One of the key tools here is spectroscopy. Hubble's spectrograph is tuned to look for signatures of common comet gases like carbon monoxide, carbon dioxide, cyanide, and water vapor. James Webb, working in infrared, can detect heat patterns and heavier molecules embedded in dust. If 3I, Atlas, behaves like a normal comet, it should show stronger gas signatures after the closed solar pass. Heat cracks open fresh ice and jets form. That's what we see with comets born in our own solar system. But early models from the Harvard-Smithsonian Center for Astrophysics suggest something different might happen. If the surface of 3I, Atlas, is unusually compact or crusted over, solar heating might not trigger the same dramatic outgassing. Instead of flaring, it could stay oddly quiet, shedding dust without the gas that usually carries it. That would match the earlier sunward pointing dust tail and the lack of clear gas detections. This kind of behavior isn't impossible. Some comets are dust-rich and gas-poor. Others become dormant over time, developing crusts that seal in volatile material. If 3I, Atlas, spent millions of years in deep space, cosmic radiation could have baked its surface into a hardened shell. Think of it like a frozen loaf of bread left out too long. The inside might still be soft, but the crust becomes tough and dry. The dust itself carries clues. Polarimetric measurements, the way light scatters off the dust grains, can hint at their size and structure. ESO teams compare these readings to known comet families. If the dust grains from 3I Atlas are more compact or metallic rich, it points to formation in a different kind of protoplanetary disk. That feeds back into models of how planets form around other stars. Not every solar system is built the same way ours was. Then there's the speed problem. Interstellar objects don't just drift in, they arrive fast, very fast. That speed shapes what survives the journey. Smaller, fluffier bodies tend to erode away over long interstellar travel. What reaches us is biased toward tougher material. This means 3I Atlas may not represent a random sample of alien debris. It represents the survivors. The stuff strong enough to cross star systems intact. Researchers at Stanford who study radio astronomy and Bracewell probe concepts have pointed out something subtle here. If interstellar objects are naturally biased toward dense, compact bodies, then our entire picture of what exists between stars might be skewed. We may only ever see the armored fragments, not the fragile ones. That matters when people start imagining how common certain materials or structures are in the galaxy. As more data comes in, astronomers also track how sunlight changes the object's rotation. Small jets of dust and gas can act like tiny thrusters, slowly spinning an object faster or slower. This effect, known from many comets, can sometimes cause fragments or sudden changes in orientation. Monitoring the spin of 3I, Atlas before and after conjunction, helps scientists infer whether hidden jets turned on while it was out of view. Even if we didn't see the jets, their fingerprints might show up in how the object tumbles afterward. All of this feeds into a larger question about how common interstellar visitors really are. The Vera Rubin Observatory is expected to detect far more of these objects in the coming years. Its wide field survey will sweep the sky repeatedly, catching fast-moving faint specks that older surveys missed. 3I. Atlas might feel rare now, but it could be the start of a steady stream of discoveries. That changes the emotional tone of stories like this. Right now, each interstellar object feels special, almost mythical. But if Rubin starts finding one every year or two, the mystery shifts from, wow, what is this? To, okay, what does the population look like? Patterns emerge. Statistics replace surprise. The unknown becomes something we can measure. Still, for now, 3I Atlas sits in that awkward space between data and imagination. It's real, it's strange, and it's limited by what we can see. The blind spot near the sun forces scientists to work backward, piecing together clues from what changes afterward. This isn't conspiracy, it's the everyday frustration of astronomy. We study the universe from one small moving platform, with fragile tools and narrow windows of visibility. And yet, even within those limits, this visitor from another star system is teaching us something simple and powerful. The space between stars is not quiet. It is busy, messy, and full of travelers shaped by violent beginnings we are only starting to understand. Once astronomers line up 3I, Atlas, beside the two interstellar visitors we've already met, a pattern starts to form. In 2017, Oumuamua rushed through the solar system on a hyperbolic path, surprising everyone with its lack of a classic comet tail and its strange, non-gravitational acceleration. In 2019, 2I, Borisov, followed much more familiar in behavior, venting gas and dust like a textbook comet. Now 3I, Atlas, sits somewhere in between. It throws dust, but not the gas we expect. It brightens, but in ways that don't fit neat models. Put together, these three tell us something uncomfortable. Interstellar objects don't come in one simple type. They're a mixed bag, shaped by different birthplaces and different histories. Researchers at the Harvard-Smithsonian Center for Astrophysics have been digging into this comparison because the differences matter more than the similarities. Oumuamua showed non-gravitational acceleration without obvious gas jets. Some teams, including scientists who analyze Arecibo legacy data, argued this could be explained by outgassing of hydrogen or nitrogen ice, substances hard to detect with our instruments. Borisov, on the other hand, was rich in carbon monoxide and behaved like a classic comet from the outer solar system, just born around another star. If 3I, Atlas, ends up dust-rich and gas-poor, it becomes the third data point in a set that says interstellar visitors span a wide range of compositions and structures. This variety changes how we think about planet formation in other star systems. Our own comets formed in a cold disk around the young sunday, but stars form in crowded nurseries. Their disks can be hotter, more chaotic, richer in metals, or blasted by radiation from nearby massive stars. The debris they eject into interstellar space carries those fingerprints. So when 3I, Atlas, passes through, it's like a foreign accent in a conversation. You can hear that it's different, even if you don't yet know the language. The European Southern Observatory has been comparing dust properties from 3I, Atlas, with dust seen in protoplanetary disks around young stars. Some of those disks show grains that are larger and more compact than what we see in our own comet families. If 3I, Atlas, dust matches those profiles, it supports the idea that it formed in a denser, more metal-rich environment. That would also help explain why its dust tail behaves oddly under sunlight. Bigger, denser grains respond differently to radiation pressure than fluffy, ice-coated dust. Another angle scientists care about is erosion. Interstellar travel is rough. Cosmic rays, micrometeorites, and temperature swings slowly chew away at surfaces. By the time an object reaches us, it may have lost much of its original outer layer. The crust we see could be a radiation-baked shell, not a fresh face. This matters because what we measure might be the scar tissue of the journey, not the true interior composition. James Webb's infrared readings can hint at what lies just beneath the surface by detecting subtle heat flows as the object warms and cools. If heat penetrates slowly, it suggests a dense, insulating crust. If it flows quickly, the surface might be porous. Then there's the question of how many of these objects are out there. Models from NASA's Jet Propulsion Laboratory suggest the Milky Way could be littered with trillions of rogue comets and asteroids flung out during planet formation. Most never come near any star again. A tiny fraction wander into systems like ours. That means every interstellar visitor we see is a rare sample from an enormous unseen population. We're trying to understand a whole ocean by tasting 3 drops of water. This also reframes how people should think about the hype around each new object. The mystery isn't that something weird passed by. The mystery is that so many weird things probably pass by unnoticed. We only catch the brightest, fastest, or luckiest ones. As surveys improve, especially with Vera Rubin Observatory coming fully online, we'll start building a real census. Not just one-off stories, but trends. Are most interstellar objects more like Borisov or more like Oumuamua? Or does the population lean towards something closer to 3I, Atlas? That answer will shape how scientists model the debris fields of other solar systems. There's also a quiet shift happening in how astronomers plan for these encounters. Missions like Voyager taught us how to use gravity assists to tour planets. Now, some researchers are asking if future probes could be placed on standby, ready to launch quickly toward newly discovered interstellar visitors. The idea isn't to chase every object, but to be ready when one passes close enough and slow enough to intercept. That kind of rapid response mission planning is being discussed in circles connected to JPL and university labs that specialize in mission design. The technology is hard, but the motivation is strong. Catching one of these objects up close would be like holding a piece of another star system in your hands. For now, though, 3I, Atlas, remains a distant teacher. We watch its light curve, its dust behavior, its path across the sky, and we compare it to the few others we've seen. Each comparison strips away a bit of our old assumptions. Interstellar objects aren't one thing, they're many things. And the galaxy that sends them our way is more diverse than the tidy models we built when we only had our own solar system as a reference. Now let's zoom out, because 3I, Atlas isn't just a visitor from another star system. It's also a visitor from another time. When astronomers talk about where these interstellar objects come from, they're really talking about the early years of the Milky Way. Stars form in waves. Some are born in calm regions, others in violent clusters where massive stars explode and flood space with radiation. The stuff that gets thrown out of those systems carries a record of those conditions. In that sense, 3I, Atlas, is less like a rock and more like a postcard mailed billions of years ago, finally landing in our mailbox. Teams working with the James Webb Space Telescope have been looking for chemical fingerprints that point to ancient origins. Certain ratios of isotopes, like deuterium to hydrogen in water ice, act like timestamps. They change depending on temperature and radiation in the birth environment. If 3I, Atlas shows ratios very different from comets formed near our sun, that suggests it grew up around a star with a different chemical history. That's the kind of detail researchers at the Harvard-Smithsonian Center for Astrophysics care about, because it helps map how chemistry varied across the galaxy long before our solar system existed. This connects to a bigger story about how the Milky Way built itself. Older stars, especially those in the thick disk of the galaxy, formed when the galaxy was younger and more chaotic. Their planets and debris formed from gas that had fewer heavy elements than what our sun had access to. If 3I, Atlas, carries signatures of that older chemistry, then we're literally seeing leftovers from an era before Earth was even a sketch on the universe's drawing board. That's wild to think about. We're not just studying space, we're studying deep time. Observatories like Keck in Hawaii have spent years measuring the chemistry of distant protoplanetary disks. They see that disks around young stars today already look different from what models predicted decades ago. Some are richer in carbon, some in oxygen, some in metals. Interstellar visitors like 3I, Atlas let us test those disk observations in a hands-on way. Instead of inferring composition from faraway light, we watch a chunk of that disk material drift right past us. There's also a lesson here about survival. For an object to cross interstellar space and remain intact, it must be tough. Radiation slowly breaks molecular bonds. Impacts with dust grains at high speeds sandblast the surface. Temperature swings, crack, and stress materials. If 3I, Atlas, is still coherent after what could be hundreds of millions or even billions of years in transit, that tells us something about how durable some planetary debris can be. It means the galaxy is full of long-lived fragments, quietly drifting between stars, carrying records of ancient systems long gone. That durability matters for another reason. It shapes how scientists think about panspermia, the idea that life's building blocks can spread between star systems. No one is saying 3I, Atlas, is alive. But if complex organic molecules can survive this kind of journey, then the raw ingredients for life might be more mobile than we once thought. Researchers using data from Webb and from ultraviolet observatories run by NASA and ESA look for amino acids, simple sugars, and other organics in comet-like bodies. If interstellar objects can preserve those compounds, then star systems aren't as chemically isolated as we imagined. They're more like neighbors, swapping seeds over a long fence. This doesn't mean life is hopping between stars like a game of catch. Space is still brutal. Most molecules break down over time. But the fact that any survive at all shifts the odds slightly. It tells us the galaxy has ways of sharing material, even if it takes millions of years and a lot of luck. That idea changes how scientists at places like Stanford and Caltech think about the early distribution of complex chemistry in the Milky Way. The galaxy might not just be a collection of isolated labs. It might be a slow, messy network of chemical exchange. As 3I, Atlas, moves on, it becomes another data point in a growing archive of galactic history. Hubble's spectrograph records, Webb's infrared scans, and ground-based telescope measurements from ESO and Keck all layered together into a picture that's still fuzzy, but getting clearer. Each interstellar visitor sharpens that picture. Each one tells us a little more about where planets form, how debris escapes, and what survives the long dark between stars. And here's the part most people miss. This isn't just about this one object. It's about what comes next. The Vera Rubin Observatory is designed to scan the entire sky again and again, catching faint, fast-moving objects we used to miss. That means 3I Atlas may soon stop feeling rare. In the next decade, we might spot dozens of interstellar visitors. When that happens, the story won't be about one mystery rock. It'll be about patterns. And patterns are where science stops guessing and starts knowing. There's a frustrating truth about astronomy that most people don't think about. Some of the most important moments happen when we can't see a thing. When an object passes too close to the sun from our point of view, the glare washes out every camera we have. Even space telescopes like Hubble and the James Webb Space Telescope have safety limits. Point them too close to the sun and you risk frying sensitive instruments. So when 3I Atlas slips behind the sun, scientists don't get drama, they get silence. This solar conjunction window is where rumors tend to grow. From the outside, it looks like secrecy. In reality, it's physics and safety rules doing their thing. NASA's Jet Propulsion Laboratory deals with this problem all the time when tracking spacecraft. Mars missions go dark for weeks during conjunction because radio signals get scrambled by the sun's plasma. It's the same idea here. The signal-to-noise ratio drops to junk. Data becomes unreliable. And unreliable data is worse than no data at all. So what do astronomers do when the main target disappears behind the sun? They prepare like chess players. They plan observations before the blackout and set up monitoring for the moment the object comes back into view. Teams at the European Southern Observatory and Keck Observatory coordinate schedules so that as soon as 3I Atlas clears the glare, telescopes are already pointed and ready. They don't want to miss the first hints of change. That's when comets and comet-like bodies often show their true nature. Heat stress peaks near the sunday. If something is going to crack, vent, or flare, that's when it happens. There's another trick scientists use during blackout windows. They don't just stare at where the object should be. They watch the space around it. Instruments look for changes in the solar wind, for tiny dust trails that drift out of the sun's glare, and for subtle shifts in the background light that might hint at material shedding. Webb's infrared instruments can sometimes pick up heat from dust clouds, even when the main nucleus is too close to the sun to observe directly. It's like watching footprints when the person is hidden behind a wall. This is where older data becomes gold. Astronomers dig into archives from Hubble spectrograph records and even legacy radio observations from Arecibo. They compare how previous comets behave during conjunctions. Some come out shattered, others come out quieter. A few surprise everyone by becoming more active after perihelion, as if the heat unlocked fresh pockets of volatile material inside. These patterns help set expectations for what 3I Atlas might do next. The blackout also forces scientists to lean on spacecraft that have different viewing angles. Probes like Mars orbiters, managed with help from NASA's JPL, can sometimes catch glimpses that Earth-based telescopes can't. It's not perfect. The geometry rarely lines up cleanly, but even a partial view from a different angle can confirm whether the object survived its close brush with the sun or changed shape in some noticeable way. There's a deeper lesson in this waiting game. Astronomy isn't just about seeing, it's about patience. You set up a plan, you collect what you can, and then you live with the gaps. The universe doesn't care about our schedules. It doesn't pause to give us a better angle. It moves on its own terms. Scientists at places like the Harvard-Smithsonian Center for Astrophysics talk about this a lot. The hardest part of space research isn't building the telescope. It's accepting that you'll never have a perfect view. When 3I Atlas comes back into view, that's when the real test begins. Did it brighten? Did it fade? Did the tail change shape? Did the spectrum shift, hinting at new gases or dust released by the sun's heat? Those answers tell us more about what it's made of than any single snapshot ever could. The before and after comparison is the story. And this is where expectations collide with reality. People hope for fireworks. Scientists hope for clean data. If nothing dramatic happens, that's still a result. It means the object is tougher, more stable, or less volatile than expected. If something dramatic does happen, then the models get stress tested. and some of them will break. That's how progress works. You put your ideas under heat and see which ones survive. There's a hard wall every space mission runs into, and it's not imagination, it's speed. And 3I, Atlas, is moving through the solar system at a pace that makes our fastest spacecraft look slow. Even with gravity assists, slingshots around planets, and years of planning, we can't just turn a probe and chase it down. Missions like Voyager 1 took decades to build momentum with carefully planned flybys. 3, Atlas didn't wait for our schedules. It arrived already moving fast. Engineers at NASA's Jet Propulsion Laboratory have run the numbers. To intercept an interstellar object on the fly, you need launch windows that open years before the object is even discovered. By the time telescopes spot something like 3I, Atlas, the geometry is already wrong. The fuel cost to catch up would be absurd. You'd need propulsion systems we don't have yet. Even experimental concepts at Stanford, inspired by ideas like Ronald Bracewell's old interstellar probe discussions, are still just that, concepts. This isn't the first time we've had to admit defeat on timing. When Oumuamua zipped through in 2017, the realization came too late to mount a mission. By the time proposals were on the table, it was already leaving the inner solar system. The same story repeated with Borisov in 2019. We watched, we learned what we could from afar. Then it was gone. The Vera Rubin Observatory is meant to change that by spotting fast movers earlier. But even early detection doesn't magically give us faster rockets. So what can we do instead of chasing? We squeeze every drop of information out of light. Spectroscopy tells us what 3I, Atlas, is made of by breaking its glow into colors. Infrared data from the James Webb Space Telescope can hint at heat and hidden ices. Polarimetry helps scientists at the European Southern Observatory figure out whether the surface is dusty, icy, or more compact. Radar methods, refined over decades of Arecibo legacy data, can estimate size and rotation when geometry allows. It's remote sensing detective work. No samples, just clues. This limitation changes how scientists think about interstellar visitors. Instead of asking how to grab one, they ask how to be ready for the next one. There's serious talk now about rapid response missions, small probes stored on standby, waiting for a launch order the moment a fast object is detected. Think of it like fire trucks waiting in a station. The problem is cost and politics. Space agencies don't love funding missions that might sit unused for decades. But discoveries like 3I, Atlas, make that argument harder to ignore. There's another angle people don't like to hear. Even if we could intercept something like 3I, Atlas, should we? Spacecraft get dirty. They carry Earth microbes, no matter how clean we try to make them. Planetary protection rules exist to avoid contaminating places like Mars or Europa. If interstellar objects carry chemistry from other star systems, slamming a probe into them risks mixing things that have never met before. Scientists at places like the Harvard-Smithsonian Center for Astrophysics worry about this more than sci-fi fans do. Curiosity is powerful. So is responsibility. All of this forces a humbling thought. We are observers, not players, in this moment. The universe throws a rare visitor through our neighborhood, and all we can do is watch the headlights fade. It's a reminder of scale. We build billion-dollar telescopes. We map galaxies. But when something unexpected rushes by, we're still stuck on the sidewalk, waving as it goes past. That sense of smallness isn't defeat, it's fuel. It pushes engineers to think about faster propulsion, about solar sails, nuclear thermal engines, and light-driven probes. Teams working with data from Keck Observatory and NASA centers are already sketching what a future interstellar interceptor might look like. Not to chase 3I, Atlas, but to be ready when the next one shows up. And the next one will show up. The Milky Way is full of debris from planet formation around other stars. Every once in a while, a piece wanders into our solar system. Each one is a message in a bottle from somewhere else. We can't open this bottle. We can only read the label. It's tempting to think the universe suddenly got crowded. One strange visitor in 2017, another in 2019, and now 3I, Atlas. To the human brain, that feels like a pattern. But to astronomers, it's more like a flashlight finally turning on in a dark room. For most of history, we couldn't see small, fast-moving objects unless they came very close and got very bright. Our sky surveys were slow. Our cameras were limited. A lot of things slipped by unnoticed. The reason these interstellar visitors feel new is simple. Our eyes got better. Projects run through the European Southern Observatory, upgrades at Keck Observatory in Hawaii, and now the wide field surveys from the Vera Rubin Observatory have changed the game. We're scanning the sky deeper, wider, and faster than ever before. There's also a timing factor most people don't realize. The sun is not sitting still. Our solar system is moving through the Milky Way at about 220 kilometers per second as it orbits the galaxy's center. Over millions of years, we pass through denser and thinner regions of interstellar debris. Think of it like driving through patches of fog on a highway. Sometimes there's nothing. Sometimes you hit a thicker cloud. It's possible our current galactic neighborhood simply has more loose material drifting around, and that raises the odds of visitors wandering in. Another reason is math. Astronomers at the Harvard-Smithsonian Center for Astrophysics have modeled how many interstellar objects should be passing through the inner solar system at any given time. The number suggests that objects the size of Oumuamua could pass through every year. We just didn't notice them before. Larger ones, like Borisov, are rarer, maybe once every few decades. Something the scale of 3I Atlas could be even rarer. The fact that we're seeing one now doesn't mean the universe changed. It means our filters improved. This also explains why each new visitor feels more shocking than the last. Oumuamua forced scientists to rethink how solid objects can behave without obvious gas jets. Borisov showed us that interstellar comets can look familiar, but still break apart in strange ways. Now 3I. Atlas is pushing questions about size, speed, and how different a visitor from another star system can really be. It's not that space got weirder, it's that our expectations were narrow. There's a quiet shift happening in how scientists talk about this. 10 years ago, interstellar objects were theoretical. Now they're a category. There are working groups. There are dedicated pipelines and survey data looking for things moving too fast to belong here. NASA's Jet Propulsion Laboratory tracks their orbits. Teams compare spectra with Hubble spectrograph records and James Webb data to see how alien chemistry differs from what formed around our sun. This is becoming routine science, even if the headlines make it feel dramatic. And here's the uncomfortable part. The more we look, the more likely it is that we'll find something that truly doesn't fit any natural model we have. That doesn't mean aliens. It means our models are built on limited examples. We've studied comets and asteroids born in one solar system. Interstellar objects come from thousands of different star systems, each with its own chemistry, heat, history, and chaos. Some will look normal. Some will look wrong. Science grows by meeting the wrong-looking thing and figuring out why it exists. There's also a cultural effect. The first interstellar visitor happened in a time of social media, instant headlines, and click-driven news. Every odd data point becomes a mystery story. That pressure can warp how people read normal scientific uncertainty. When researchers say, "we don't know yet," it gets translated into, "they're hiding something." In reality, slow, boring analysis is what usually leads to the truth. Teams working with data from places like the European Southern Observatory and JPL spend months just checking their own instruments before they even start speculating about big ideas. So the pattern we're seeing isn't a cosmic invasion. It's a human one. We invaded the dark with better eyes. Now the dark is answering by showing us how much was always there. The big shift is this. We're moving from a time when the solar system felt like a closed neighborhood to a time when it feels like a street in a busy city. Things pass through. Most don't stop. A few leave us with questions that take years to untangle. When scientists talk about what 3I Atlas is made of, they're really asking a bigger question. What do other star systems make their small bodies out of? Because comets and asteroids are leftovers. They're scraps from planet building. They carry the fingerprints of the environment they formed in. With 3I Atlas, Teams working with the James Webb Space Telescope started by looking at its heat pattern and faint infrared glow. Webb doesn't just take pretty pictures. It breaks light into colors that reveal chemistry. Early readings showed water ice in the coma, which already tells us something important. Water isn't rare in the universe, but the way it forms depends on temperature and radiation near the parent star. If the water ice on 3I, Atlas, formed far from a cooler red dwarf star, its structure could look different than water ice formed around a star like our sun. Then comes the deuterium to hydrogen ratio. This is one of those nerdy details that actually carries huge meaning. The ratio acts like a chemical accent. Water from different parts of the galaxy carries slightly different ratios. Scientists at NASA's Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics have used this ratio to trace where comets in our own system likely formed. If 3I, Atlas, shows a ratio far from anything we've measured before, that's a clean proof it grew up around a very different kind of star. It's like finding a fossil with DNA that doesn't match any family tree we know. There's also the dust. The color and reflectivity of the dust tell us about minerals. Observations tied together from the European Southern Observatory and Keck Observatory suggest the grains are darker and less reflective than most comets we see here. That points to carbon-rich material. Carbon-rich dust forms in colder, more chaotic environments where radiation bakes organics into complex chains. In simple terms, 3I Atlas might be carrying chemistry that's older and more processed than what we usually see drifting around our sun. What makes this exciting isn't the idea that it's alive or engineered. It's that it's foreign in a way we can measure. This is the first time we can study raw material from another star system without sending a probe. It's like a sample return mission that nature delivered to our doorstep, moving too fast for us to catch, but slow enough to scan with light. Scientists also look at how the surface responds to sunlight. Comets from our system often develop jets as ice warms and turns to gas. With 3I, Atlas, the activity looks uneven. Some regions brighten, others stay dark. That suggests a surface that's layered, maybe coated in ancient material, hardened by billions of years of radiation in deep space. Hubble spectrograph records, compared with newer Webb data, show this kind of layering can change how an object heats up and cools down. It's a clue to how long it's been drifting between stars. There's another quiet detail that matters: the speed. 3I. Atlas is moving too fast to be from our sun's family. Its velocity matches what you'd expect from debris ejected during planet formation around another star. When giant planets shift early in a system's life, they fling smaller bodies out like gravel from a tire. Some of those bodies wander the galaxy for billions of years before falling into another system by chance. The fact that we're seeing one now gives us a real data point for how common that process is. All of this points to a simple but powerful idea. 3I. Atlas isn't strange because it's hiding something. It's strange because it's honest. It's showing us what other star systems actually produce when they build planets. And that helps scientists test whether our own solar system is typical or a weird exception. The moment 3I, Atlas, slips behind the sun is the moment every astronomer dreads. Not because something bad is guaranteed to happen, but because it creates a blind spot at the exact point when this object is under the most stress and the most interesting physics usually shows up. When an interstellar object dives close to the sun, a few things normally happen. The surface heats fast. Ice starts turning into gas. Cracks open. Jets fire off. Sometimes the body fractures. That's when we learn the most about what's inside. This is how we learn so much from comets in our own system, using decades of Hubble spectrograph records and ground-based observatories like the Keck Observatory in Hawaii. The problem is, with 3I, Atlas, that critical moment happens when the sun is between it and Earth. The glare is so strong that even space telescopes struggle to get clean data without risking damage to their instruments. Teams at NASA's Jet Propulsion Laboratory ran simulations of what we might miss. If 3I, Atlas, were to release a large burst of gas, crack apart, or change its spin, the best evidence could happen while we're blind. That's frustrating, but it's also part of astronomy. The universe doesn't schedule its best moments around our camera angles. This blind window is why there's been so much noise online. People see the gap in observation and assume it means secrets, cover-ups, or hidden events. In reality, it's geometry. The sun is a wall of fire and radiation. Pointing delicate sensors straight at it is like aiming a microscope at a welding torch. The James Webb Space Telescope, for example, has strict limits on where it can look to protect its mirrors and instruments. The same goes for Hubble and most Earth-based telescopes. What scientists try to do instead is prepare for the before and after. Before 3i, Atlas vanishes behind the sun. They measure its brightness, rotation, gas output, and trajectory as precisely as possible. That gives a baseline. After it reappears, they measure again. Any changes can be traced back to what likely happened during the blind window. This method has been used before. It's how astronomers studied comets that pass close to the sun using data gaps long before we had modern space telescopes. There's also a backup plan. Observatories positioned away from Earth's line of sight can sometimes get partial views. The European Southern Observatory and networks linked to the Vera Rubin Observatory coordinate timing to catch the object at low angles, just as it emerges from solar glare. Even Voyager 1 telemetry data, while not designed for imaging, helps map background radiation and solar wind conditions during the same period. That context matters when scientists interpret what they see later. The fear people feel during this blind spot is human. When something unknown disappears from view, our brains fill the gap with stories. But the truth is simpler and less dramatic. The object keeps moving. Physics keeps working. We just lose the front row seat for a short time. What matters is what 3i Atlas looks like when it comes back into view. If it looks the same, that tells us it's structurally tough. If it's dimmer, brighter, or fragmented, that tells us how it handles stress from a star that isn't its home. Either outcome is valuable science. And here's the quiet part most headlines skip. Even if nothing dramatic happens during the blind window, the data we've already collected is enough to reshape how scientists think about interstellar debris. One confirmed visitor like this forces updates to models used at places like the Harvard-Smithsonian Center for Astrophysics and Stanford research groups working on detection theory, including ideas inspired by Ronald Bracewell's old concepts about interstellar probes. Not because this object is a probe, but because detection limits matter when you're trying to separate rare natural objects from everything else the galaxy throws at you. When astronomers line up the 3 interstellar visitors we've seen so far, Oumuamua in 2017, 2i, Borisov in 2019, and now 3i, Atlas, a pattern starts to form that's easy to miss if you only look at headlines. At first glance, they seem totally different. Oumuamua had no obvious gas tail and showed strange acceleration as it left the solar system. Borisov looked more like a classic comet, with gas and dust behaving in ways scientists expected. Now 3i, Atlas, sits somewhere in between, showing dust activity but with unusual angles and behavior that don't fit neatly into either category. The simple truth is this: interstellar objects are not one type. They're leftovers from other star systems. And other star systems don't all build planets and debris the same way ours does. Researchers at the Harvard-Smithsonian Center for Astrophysics and teams working with the European Southern Observatory have pointed out that each of these visitors likely formed around very different stars under very different conditions. Some stars are metal-rich, some are poor in heavy elements, some have violent early histories with massive planets flinging debris into deep space. When those systems shed material, it wanders the galaxy for millions or billions of years before stumbling into places like our solar system. Oumuamua taught astronomers that not all interstellar objects will behave like comets we know. Its non-gravitational acceleration forced teams at NASA's Jet Propulsion Laboratory to rethink how tiny forces, like outgassing from unusual ices or even hydrogen release, could push small bodies without leaving obvious tails. Borisov, on the other hand, helped confirm that some interstellar visitors really are normal comets just born somewhere else. Its chemical fingerprints, measured with Hubble spectrograph records and large ground telescopes like Keck in Hawaii, showed familiar patterns, just in different ratios. 3I. Atlas adds a third data point. And in science, 3 points are the start of a trend. It tells astronomers that the space between stars might be far more crowded with wandering debris than we once thought. For decades, people assumed interstellar objects passing through our system would be once-in-a-lifetime events. Now, with better surveys and tools like the Vera Rubin Observatory coming fully online, scientists expect these detections to become more common. We didn't suddenly get lucky 3 times in a row. Our eyes just got better. This changes how scientists think about risk too. Not because 3I Atlas is a threat, but because interstellar objects move fast and don't follow the same population models as asteroids from our own system. Planetary defense teams at NASA, JPL, and international partners are updating their models to include fast-moving visitors that don't originate from predictable regions like the asteroid belt or Kuiper belt. It's a small shift in policy, but a big shift in mindset. The solar system isn't closed, it's an open highway. There's also a deeper scientific payoff. Each interstellar object is like a free sample return mission from another star system. We don't have to build a spacecraft to go there. The galaxy brings pieces of itself to us. By studying their chemistry, scientists can test theories about how planets form around different types of stars. Data from the James Webb Space Telescope and future infrared observations will help identify ices and organics that may never form around our sun, giving researchers clues about how common water, carbon compounds, and other building blocks might be across the Milky Way. And here's the part that quietly humbles a lot of people. None of this requires aliens, secret programs, or hidden agendas to be fascinating. The universe is already weird enough. Stars throw out their leftovers, gravity, slingshots, debris across the galaxy. Every now and then, one of those leftovers wanders into our neighborhood. And for a brief moment, we get to study a piece of another world's history. When scientists talk about interstellar visitors like 3I, Atlas, they're not just excited about the rock or ice itself. They're excited about what it carries. Every comet or fragment that drifts in from another star system is a time capsule. It formed in a different place, around a different sun, under different chemistry. That makes it a rare chance to test one of the biggest questions in science without leaving home. How common are the building blocks of life in the galaxy? Teams working with the James Webb Space Telescope are especially focused on the faint chemical fingerprints in the coma and tail of 3I Atlas. Infrared spectroscopy can pick out water ice, carbon monoxide, carbon dioxide, and more complex organics. Hubble spectrograph records and ground-based data from Keck Observatory in Hawaii help cross-check those findings in visible and ultraviolet light. When these instruments agree, scientists can be confident about what's really there, not just what they hope to see. Why does this matter? Because if the same basic chemicals keep showing up in objects from totally different star systems, it means the galaxy is good at making the ingredients for life. Not life itself, but the raw parts, carbon chains, water, simple organics. Researchers at the Harvard-Smithsonian Center for Astrophysics have pointed out that many of these molecules form in cold clouds between stars long before planets even exist. By the time stars and planets form, the chemistry is already preloaded. Interstellar objects are basically delivery trucks carrying that chemistry across the galaxy. This idea ties into an old debate called panspermia, the notion that the seeds of life could spread from one system to another on rocks and comets. Most mainstream scientists are careful with this idea. They don't say life itself is traveling around the galaxy, but they do say that the ingredients might. NASA's Jet Propulsion Laboratory has studied how organic molecules can survive long periods in deep space, shielded inside ice and dust. Some compounds break down under radiation, others are surprisingly tough. That means interstellar visitors could be moving complex chemistry between star systems, slowly enriching young planetary systems with the stuff life might later use. There's also a practical side to this research. By comparing the chemistry of 3I, Atlas, with that of comets born in our own solar system, scientists can learn how unique or typical our system really is. If the ratios of water to carbon compounds look similar, It suggests that planet-forming disks across the Milky Way might follow similar rules. If they're wildly different, it hints that some systems might be better factories for life-friendly chemistry than others. Data from ESO's Very Large Telescope and upcoming observations from the Vera Rubin Observatory will help map how common these interstellar visitors are and how varied their compositions might be. Another layer to the story is time. Some interstellar objects are likely far older than our solar system. They may have formed billions of years before Earth existed. Studying them is like peeking into the early chapters of the galaxy's story. It helps astronomers test models of how dust grains grow, how ice forms in cold disks, and how young planetary systems eject material into interstellar space. In a quiet way, 3i, Atlas is helping scientists check their homework about how stars and planets grow up. So while headlines focus on mystery and shock, the real value of 3i, Atlas, is steady, patient science. It's a reminder that the universe is constantly mixing itself, trading material between star systems, blurring the lines between here and there. Our solar system isn't isolated. It's part of a giant, slow exchange program run by gravity. For most of human history, interstellar visitors were pure theory. We assumed bits of rock and ice had to be drifting between stars, but we had no proof. Now that objects like 3i, Atlas exist in our data, the big shift is not just what we've seen, but what we're about to see next. We're standing at the start of an era where these visitors won't be rare surprises anymore. They'll become part of the normal sky. This change is coming because of how we're building our eyes on the universe. The Vera Rubin Observatory in Chile is designed to scan the entire visible sky again and again, night after night. Its wide field camera will catch fast-moving, faint objects that older surveys missed. That means interstellar objects will no longer slip through unnoticed. Instead of spotting one every few years, scientists expect to find several each year, maybe even dozens over time. Not all of them will be dramatic. Many will be small, dim, and boring. But that's actually good news. Patterns only become clear when you have lots of examples. As more interstellar objects are found, researchers at places like the Harvard-Smithsonian Center for Astrophysics and NASA's Jet Propulsion Laboratory can start building real statistics. Are most of them icy, like comets? Are some rocky, like asteroids? Do their shapes and spins look random? Or do they fall into common types? With enough data, scientists can test ideas about how often star systems eject material into interstellar space and what kinds of objects survive the trip. There's also talk about something even more ambitious. Not just watching these visitors, but chasing them. After the surprise of Oumuamua and Borisov, mission planners started sketching ideas for fast response probes. The concept is simple on paper and brutal in practice. You detect an interstellar object early, then launch a small spacecraft that can catch up to it, or at least pass close enough to take detailed images and measurements. Engineers at NASA JPL and researchers at Stanford have discussed solar sail concepts and high-energy propulsion ideas that could, in theory, make this possible. It's not science fiction anymore. It's an engineering challenge waiting for funding and the right timing. If such a mission ever flies, the payoff would be huge. Instead of guessing what an interstellar object is made of from far away, we could see its surface up close. We could measure its magnetic field, taste its dust, and watch how it reacts as it warms near the sun. That kind of data would rewrite textbooks. It would tell us how common different kinds of building blocks are in the galaxy, and whether the chemistry that led to life on Earth is rare or ordinary. There's a deeper shift here too, one that goes beyond science. The more interstellar objects we find, the harder it is to think of our solar system as a closed bubble. We live in a stream of material that moves between stars over millions and billions of years. The Voyager 1 spacecraft, now out in interstellar space, is measuring this environment directly. Its data on cosmic rays and magnetic fields shows that the space between stars is not empty. It's active. It's full of energy and particles moving in slow, vast patterns. Interstellar objects are part of that flow, like driftwood in a cosmic ocean. This changes how we think about origins. Earth may feel unique, But the chemistry that made our oceans, our air, and eventually life itself may be part of a much wider recipe used all over the galaxy. When 3I, Atlas, passed through, it wasn't just a visitor. It was a reminder that we're part of a much larger system of exchange, one that's been running long before humans existed and will keep running long after we're gone. As 3I, Atlas, races toward its closest pass by the sun, every major observatory is in a quiet countdown. The problem is simple and brutal. This is a once-only chance. After it swings around the sun, it will gain speed and head back into interstellar space. There will be no second visit, no do-over. Whatever data we collect in this narrow window is all humanity will ever have from this object. Teams at the European Southern Observatory are lining up time on the Very Large Telescope to squeeze out every photon they can. The James Webb Space Telescope has to work around strict safety limits when pointing near the sun, so its observations are carefully planned, short, and precious. Hubble spectrographs are being used to break the light from 3I, Atlas, into fine detail, looking for the fingerprints of water, carbon compounds, and more exotic ices. Each instrument sees a different layer of the story. Put together, they form the closest thing we'll get to an autopsy of a traveler from another star. One of the biggest questions scientists want to answer is how old this object really is. Interstellar space is harsh. Cosmic rays slowly damage surfaces. Ultraviolet light breaks chemical bonds. Over millions or billions of years, these effects leave scars. By studying how altered the surface of 3I, Atlas, appears, researchers can estimate how long it has been drifting between stars. That tells us something about how often star systems throw material out into the galaxy and how long those fragments survive before they're destroyed. Another focus is rotation. Observatories like Keck in Hawaii are tracking tiny changes in brightness over time to map how fast 3I, Atlas spins and how regular that spin is. A smooth, steady spin hints at a solid, cohesive body. A wobble or irregular pattern could mean it's a loose pile of rubble barely holding together. That difference matters because it tells us how these objects form and how violent the events are that eject them from their home systems. Then there's the tail. If 3I, Atlas, shows gas jets as it warms, spectrographs can measure exactly what's coming off its surface. Carbon monoxide, carbon dioxide, water vapor, maybe even traces of more complex molecules. The ratios of these gases act like a chemical passport. They point back to the kind of star system it formed in. Astronomers at the Harvard-Smithsonian Center for Astrophysics are especially interested in comparing these ratios with what we see in comets from our own solar system. Similarities would hint that planetary systems across the galaxy share common chemistry. Big differences would mean there are many ways to build a world. There's also a race against brightness. As 3I, Atlas, gets closer to the sun, it becomes harder to observe safely because of glare and heat. There's a narrow sweet spot where it's bright enough to study in detail, but not so close to the sun that telescopes have to turn away. Miss that window, and key information is gone forever. This is why planning these observations looks less like calm research and more like air traffic control. Every minute counts. What makes this tense is that some of the most interesting changes might happen right at closest approach. Comets can suddenly flare, crack, or shed fresh material when the sun heats them up. If 3I, Atlas, does something unexpected at perihelion, we might catch the moment it reveals its true nature. Or we might miss it entirely because the sun blinds our view. That's the gamble of astronomy. The universe doesn't wait for our schedules. The tension peaks when the last clean window closes, and 3I, Atlas, slips into the glare of the sun. For days, the most powerful eyes we have are forced to look away. Then, the delayed data finally lands. Deep inside the stream from the James Webb Space Telescope, analysts at NASA's Jet Propulsion Laboratory notice something that doesn't fit the models. The heat profile isn't smooth like a normal comet warming up. It spikes, steadies, then spikes again in tight intervals, as if parts of the surface are turning on and off. Hubble's spectrograph shows uneven releases of carbon monoxide and carbon dioxide that don't line up with simple ice melting. At the European Southern Observatory, the Very Large Telescope picks up brief flashes in narrow wavelengths that fade too fast to be random glare. When teams compare notes across time zones, the pattern becomes impossible to ignore. 3I. Atlas is not just shedding material. It is reacting to the sun in a way no natural object we've studied ever has. Even the cautious voices admit this visitor is forcing new questions. Is this a rare type of comet formed in extreme conditions around another star, or are we seeing chemistry and structure the textbooks don't cover yet? Either answer is huge. If it's natural, then the galaxy is making things far stranger than we imagined. If it's not, then the universe just crossed a line we were not ready for. When the object reappears from behind the sun, it looks changed. Its brightness curve is different. Parts of its tail are thinner, as if something was burned away. The gas ratios measured by Keck in Hawaii don't match what they were before perihelion. Something happened in that hidden moment, and we can only piece it together from the clues left behind. Researchers at the Harvard Smithsonian Center for Astrophysics call it a reminder that the universe doesn't reveal its secrets cleanly. Sometimes it gives you fragments and makes you live with the gaps. 3I. Atlas will keep moving faster now, slipping past Jupiter's region and back toward the dark between stars. We won't chase it. Voyager 1, already far beyond the planets, can't turn around. Webb will move on to other targets. The data we gathered becomes the only record of this meeting. Years from now, students will study these spectra, these light curves, these odd heat spikes, and realize this was the moment our picture of interstellar visitors grew up. Not because we solved the mystery, but because we learned how much we still don't know. If this report made you stop and stare at the sky a little longer, stay with us and watch the next video that's popping up now, because we're tracking what might come after 3I, Atlas, and if you don't want to miss the next strange visitor that slips into our neighborhood, hit subscribe so you're here when it happens.